SawTeen Miho Museum Bridge. SawTeen is a structural engineer who has been a practicing engineer for over 40 years. She was born and raised in Penang, Malaysia, before moving to America to study at Cornell University, where she obtained a bachelor's and master's degree in engineering. She initially started out in architecture, but switched to structural engineering due to her passion for maths and physics. Throughout her career, she has worked on many tall buildings and long span structures. Sortin C is an excellent role model. She actively encourages more female engineers to enter the profession. Miho Museum Bridge is located in the mountains near Kyoto, Japan. The bridge forms part of a journey that visitors undertake when visiting the world-renowned Miho Museum. The architect envisioned people traveling through a tunnel in the mountain and a bridge across the valley before arriving at their destination. Lira, with Sortin C as a managing partner, were hired as structural engineers due to their industry-leading reputation in elegant and highly efficient design. The bridge and museum were designed simultaneously and opened in 1997. The bridge spans 120 meters from the mountain across the valley and is a combined cable-stayed bridge. The main structural components of the superstructure are the space frame deck, the pylon and strut, and the stay cables. Steel was chosen because of its high load-bearing capacity and relatively light weight. The bridge uses an innovative load-bearing system. The space frame deck is structurally continuous with the floor of the tunnel and cantilevers over the valley, hence longitudinal compression forces develop in the main girders. The cable stays are located above and below the deck. They are post-tensioned and anchored back to the concrete tunnel to provide a net upward force on the bridge. The cables below the deck are attached to the strut and help to control deflection. At the museum side, longitudinal movement is accommodated by bearings that also provide lateral and torsional restraint. Combining multiple load-bearing systems and post-tensioning the cables reduces the overall bending moment, allowing for a shallower structure. The key drivers for this structural solution reflect the ceremonial entrance to the Miho Museum. This was achieved by using a structural form that was visible to the public when using the bridge. The steel connections were also carefully selected and detailed. Minimal impact on the local environment. It was critical that the bridge would not impact the views of the surrounding nature reserve, hence the height of the pylon was restricted. The bridge also spans a valley without any intermediate supports, reducing the impact on local ecology. Limited accessibility on site. As a result of the restricted nature of the site, prefabricated elements that could be transported through the tunnel were specified. Resilient to typhoon winds and major earthquakes. The bridge was carefully designed to resist significant lateral and torsional forces imposed under typhoon winds and earthquakes. The space frame deck helps to minimize imposed wind loading by allowing wind to flow through the structure. Majority of load transfer through tunnel side. It was necessary that the majority of loads were transferred through the tunnel side due to the high quality of underlying rock. Therefore, the pylon was positioned on the tunnel side and the cables were anchored to the tunnel. An approximate cradle-to-gate calculation for the embodied carbon has been undertaken. The embodied carbon has been calculated using the ICE database and iStruct guidelines. The tunnel has been excluded from calculations, however the volume of concrete which provides anchorage to the backstay cables has been included. The first step is to evaluate whether a bridge and tunnel are necessary. Does the carbon cost outweigh the need? There may be opportunities to allow visitors to arrive at the museum from a different angle, eliminating the need for a bridge entirely. A simple yet effective method of reducing the embodied carbon is to build less. By reducing the weight of the superstructure, the size of the substructure and foundations can also be reduced. The existing structure is highly efficient in its design. The combined stay promotes axial behavior and reduces flexural responses, making it extremely efficient. It enables a reduction in the required deck depth and amount of materials needed. The embodied carbon of the deck is further reduced as the overall diameter of each section remains constant, while the wall thickness and steel grade vary. The cables also reduce in diameter as a respective length decreases. The inclusion of an arch pylon allows for a significant reduction in cable sizes. The arch is pinned at the base to prevent additional moments. There may be opportunities to reduce the self-weight of the bridge further. However, this would make the structure more susceptible to vibrations when subjected to dynamic loading. For the footbridge to be deemed adequate, the fundamental natural frequency of the bridge must be greater than 5 Hz. Reducing the imposed loads and deck width of the bridge whilst maintaining adequate stiffness leads to a 20% reduction in embodied carbon.